In this lab, we're calculating the mass of a black hole by analyzing the motion and forces acting upon a star orbiting it. We're given the mass of the star, which is 2 times 10 to the 30 kilograms, and the time interval we're measuring at, which is 86,400 seconds. A short summary of the results shows that the magnitude of the net force is 8.56 times 10 to the 28 newtons, the magnitude of the parallel component of the net force is 1.39 times 10 to the 28 newtons, and the magnitude of the perpendicular component of the net force is 8.46 times 10 to the 28 newtons. Plugging these values into the equation I will show later, we find the mass of the black hole to be about 1.22 times 10 to the 34 kilograms. Here you can see some relevant information and equations that we can use for this lab. Firstly, we see that momentum is equivalent to mass times velocity, and the change in momentum over the change in time, or dp over dt, is equal to F net. This is derived from Newton's second law. Next, we see the formula for the gravitational force, which is equivalent to the gravitational constant multiplied by the masses of the two objects acting upon each other over the square of the distance between these two objects. Later in the lab, we will rearrange this equation to isolate for one of the masses to find the mass of the black hole. Finally, we see the formula for dp over dt is equivalent to dp over dt perpendicular plus dp over dt parallel. This is simply showing that the change in momentum is equivalent to the sum of the two components of momentum. To the left, you can see some of the initial system conditions, which include the gravitational constant, the mass of the star, and the time interval. To the right, we see the equations used for the calculations. We first find the initial and final momentum, which is done by multiplying the mass of the star times the initial and final velocity, respectively, because momentum is simply mass times velocity. We then find delta v and delta p, which is the change in velocity and change in momentum, and this is done by subtracting, respectively, the initial velocity and initial momentum from the final velocity and final momentum to find the overall change. We then find dp dt, or the change in momentum over the change in time, which is simply done by dividing delta p, or the change in momentum, by delta t, or the change in time. Finally, we assign this as equivalent to F net, because as you remember from before, F net is equal to dp dt, or the net force is equivalent to the change in momentum. Next, we have to find p hat, or the unit vector for the momentum. We can do this by dividing the initial momentum by the magnitude of the initial momentum. We then find d mag pdt, or the magnitude of the change in momentum, which is done by subtracting the magnitude of the initial momentum from the magnitude of the final momentum and dividing that by delta t. With these two values, we can find dp dt parallel by multiplying p hat by the magnitude of the change in momentum to give us the parallel component of the change in momentum. We can then assign this to F net parallel because F net is equal to dp dt, meaning that the parallel component of the net force is also equal to the parallel component of the change in momentum. Since we know that dp dt is equal to its parallel plus perpendicular components added together, we can rearrange this equation to find dp dt perpendicular, which is dp dt minus dp dt parallel. Finally, we assign this to F net perpendicular because the net force is equal to the change in momentum. Once we find all these values, we're able to rearrange the gravitational force equation and plug these values in to actually find the mass of the black hole. As you can see on line 195, we rearrange this equation to assign the variable mbh, or mass black hole, the equivalent of the magnitude of the net force multiplied by the square of the distance between the star and the black hole, divided by the gravitational constant multiplied by the mass of the star. This gives us mbh, or the mass of the black hole. To the right, you can see images of the simulation at one point in the star's orbit, as well as once the orbit is complete. The purple arrow, or the arrow representing the parallel component of the net force, always points along the star's axis of motion. The orange arrow, or the arrow representing the total magnitude of the net force, always points towards the black hole, and the blue arrow, or the arrow representing the magnitude of the perpendicular component of the net force, always points perpendicular to the purple arrow, which itself points along the axis of motion. In the second image, you can see the total orbit, which can be noted as elliptical, with the black hole decentered from the middle of the orbit. As you can see, F net is equal to dp over dt, meaning that the overall net force is equivalent to the change in momentum over change in time. However, the parallel and perpendicular components of the net force and change in momentum affect different aspects of the motion. The parallel component affects the magnitude, while the perpendicular component affects the direction. While the net force and the change in momentum over change in time are equivalent, they are calculated differently, meaning in scenarios such as this where we don't know all the values to calculate the net force, we can instead calculate for the equivalent change in momentum over change in time. Thus, we can see that while these two values and their separate components are equivalent, they are calculated differently, meaning that we can find them in different scenarios using different values. It is impossible for us in this new situation to find a number for the mass of the new black hole that is any different from the mass of the old black hole. This is because the situation seems to remain the same. The motion and mass of the star remain unchanged, the new black hole is placed in the same position as the old black hole, and the gravitational constant, by definition, is a constant. This means that all the numbers that we're plugging into the equation seem to be the same, which means that we should get the same result for the mass of the new black hole as the mass of the old black hole. In conclusion, we can see how some of the fundamental principles can be derived to find information about the forces acting upon an object, even in scenarios where we don't know all of the values needed to find this information. Because dp over dt is equal to Fnet, we were able to use the formula for dp over dt to find Fnet in this situation, and then rearrange the formula for Fnet to find the mass of the black hole. We see how the different components of the net force affect different aspects of the motion, and how the fundamental principles can be used to determine these details in multiple different scenarios. This is very useful in real life, where we don't necessarily know all the information about an object, but we have some values that we can observe.